So this is going to be one of our first kind of hardcore derivations. So I want you to pay attention and follow through how we apply, in this case, the molecular partition function and expand it into what we call the Maxwell-Boltzmann distribution. Okay, so here we go. So if you recall, the molecular partition function looks like this. So Q is the sum. And if degenerate or equivalent energy states exist, there's this degeneracy factor, right? As well as, this E raised to the power negative energy sub I corresponding to whatever state is in that sum divided by K Boltzmann T. Okay, so now we're going to expand this specifically for the translations of molecules and their kinetic energy. Okay, so I've used the letter I here, but note that that's just generic, right? So that letter is going to change. So for example, we know that kinetic energy, EK, of an object can be written as 1/2 mvx squared plus 1/2 mvy squared plus 1/2 mvz squared. So already we can kind of start to see what this whole degeneracy thing is going to give us, because motion in the x, y, or z should be degenerate for a gas. So we're going to have to take advantage of this degeneracy term. Okay, and so now I'm going to write out, using a little bit different notation, a new function here that we're going to develop. And that function is going to go as the following. I'm going to use a capital K in place of this letter G. And I'm going to write e to the negative e k divided by K Boltzmann T, where we recognize this now EK is my kinetic energy. And I'm going to go ahead and expand that. And here I'm going to use my EXP notation because this exponential is going to get a little hairy. Okay. And so that I'm going to write as, let's see, negative. I'm going to put a big parenthesis around 1/2 mvx squared plus 1/2 mvy squared plus 1/2 mvz squared, and of course all divided by K Boltzmann T, right? So note all of that is in the exponent. And now I can take advantage of a trick, an algebraic trick with exponents. So I'm going to separate those out, okay? And rewrite my function as K exp, oh, let's write K times all this stuff, okay? And that's going to be, let's see here, negative mvx squared divided by 2 kbt times exponential of negative mvy squared divided by 2 kbt times then the exponential of negative mvz squared divided by 2 kbt. Okay, and so now we can start to see that we're going to have a way of separating those degenerate states, those x, y, z states. Okay, and we'll also put some language of calculus in here so that we can use calculus. So I'll say if f of dvx, dvy, dvz is the fraction of molecules, is fraction of molecules in the range, Vx tends to Vx plus dVx, right? And Vy tends to Vy plus dVy, and then we can say the same thing about Z, okay? Vz tends to Vz plus dvz. Okay, so this is just allowing us to use the language of calculus. And so thus I can now write a function f of v total, which is going to be some product of these individual functions. All right, and then of course, that's all. So there's a times dv and times dv, right, on both sides. Okay. So for example, I can now talk about this just in terms of the z dimension by saying, for example, f of vx dvx equals, now I'm going to write this as exp negative mvx squared over 2kbt dvx. And now what about this k term? Well, because it's degenerate, we know it's going to apply evenly throughout each of those dimensions. So I'm going to write k to the 1/3 power. And so when it gets recombined into all of these individual functions, I'll get back to the original function that I had. I'm also going to note that I can say the integral from negative infinity to infinity of this function f of vx dvx integrated right from negative infinity to infinity will equal 1. And all that's saying is from negative infinity to infinity, there's 100% chance that we'll find that particle somewhere. Okay, so that's what this means. So what we've done is normalized this function to 1. And what that also allows me to do is determine the value of this constant k. So I can treat this as a normalization constant. So for example, doing some algebra, I can now say 1 equals k to the 1/3 power, because it's a constant. I'm taking it out from the integral sign. Okay, I don't need to put that in the integrand because it's a constant. And now that's going to be, replace this with f vx dvx, right, this function here. So that's going to be my exponential function of negative mvx squared to kbt times dvx. All right, fantastic. Okay, and from here, right, I know we're learning how to use Mathematica, so we could plug this into Mathematica and it could solve that function for us all day. However, I'm a huge fan of integral tables. And as it turns out, there's a standard solution for this integral, and it goes as the following, okay? When you have an integral from negative infinity to infinity of exponential negative ax squared dx, and if you compare this to this, right, they're the same. My a is m divided by 2kbt, right? Okay. Then this has a very simple form, and so the solution to this integral is pi over the constant a to the 1/2, so the square root. So now we can very simply solve this integral by just substituting what we have for a, and I'll go ahead and do that on the next slide, okay? So keep that in mind. So I'm just going to write the solution of this. So here we recognize a is m divided by 2kbt. So our solution will be pi divided by m divided by 2kbt, and we'll do the algebra to make that look a little bit nicer. Okay, so now that's going to go 1 equals k to the 1/3 power. And here I'm just going to write that integral solution with the algebra already done. 2 pi kbt divided by m all to the 1/2 power square root. So stop and make sure that you can do that algebra from the previous slide. Okay? And so from here we can solve for that constant k. And I'm going to just do the algebra very quickly. So that's just k equals m divided by 2 pi kbt, all to the 3/2 power. And I want you to note here, I'm going to give a few options. When we use a lowercase m in this class, this is very subtle. Actually, here, let me do this. Let's change colors. Yeah, let's be all slick and cool. So when I use a lowercase m, okay, that corresponds to kilogram per molecule, and thus you have to use K Boltzmann, okay? But if I use a big capital M, that corresponds to kilograms per mole, and you may have guessed it, we'll use Batman, the gas constant, right? So I'll say that's now or big capital M divided by 2 pi r t to the 3/2. So either of those are okay. It just depends what constant you're going to use. So pay attention to that in this class. That lowercase m is specifically kilogram per molecule. The uppercase m is kilogram per mole. And of course, this would give us the molar mass in terms of kilograms. Okay. So now I can go back here and I can write my function f of Vx equals that constant k raised to the 1/3 power. I'm going to go to using r, that's a capital M, 2 pi RT. Now to the 1/2 power, okay, and then that's times the exponential of negative m, capital M, right? Negative m Vx squared divided by 2RT. And so that's going to be our function for f of Vx. And of course, we can combine this now for everything. And so when I do that, I'm going to write this as f of V now. And I recognize that this constant is going to get cubed because it's got 1/3 contributions to each dimension. So now that's going to be capital M divided by 2 pi RT to the 3/2 power, all times the exponential of, let's see here, that's going to be negative capital M, just V, for Vx, Vy, Vz, squared over 2RT. And of course, if I multiply this by my volume element, dVx, dVy, dVz, then I do the same on this side, dVx, dVy, dVz. Okay? And I also recognize that in my volume element here, right, if I take the integrand from negative infinity to infinity of that volume element, dVx, dVy, should be a z. Okay, this equals the integrand of 4 pi v squared dv. And of course, if we then go and finish off that integrand, right, you get 4/3 pi v cubed, which is our volume of a sphere, right? And of course, I'm using v for velocity, but if we would replace that with r for radius, right, this is the volume element, 4 pi r cubed, all right? So now if I apply that through to my function here, I can finally write, so let's see, do I have another slide? Oops, okay. I can finally write f of v equals, and I'm just going to keep it as this integrand, right? Because you notice here that I've got to integrate this side and I've got to integrate this side. So I'm not going to have the contribution 4/3 pi v cubed. I'm going to have this contribution right here because I have the integral of each side, all right? And so finally, that's going to go as 4 pi that I get from right there, okay? And then I have this constant, capital M, 2 pi RT to the 3/2 times V squared, okay? And then times the exponential of negative capital M V squared to RT. Yes. And this equation is our Maxwell-Boltzmann distribution of velocities, okay? And we're going to play with this equation a lot in the coming weeks in your Mathematica slides, okay? And so there's a few